Howdy. And so what have we learned? We learned that having noble gas configuration is extra stable because noble gas configuration corresponds to having full subshells. We've learned that elements tend to gain, lose, or share electrons to get noble gas configuration. We've learned that Lewis electron dot diagrams enable us to determine if electrons are bonding electrons or non-bonding electrons. And we've learned that Lewis electron dot diagrams do not yield accurate bond angles or bond shapes, but are the first step in determining the shape of the molecule. And so in this video, we're going to talk about molecular shapes and VSEPR theory. Now, molecular shapes greatly affects a molecule's chemical and physical properties. For example, enzyme activity is typically based on a molecule shape. Whether or not a molecule is polar or non-polar depends on its shape. Polarity of molecule affects its solubility, viscosity, melting point, boiling point, etc. VSEPR theory gives us a simple way of determining a molecular shape. And so molecular shapes are very, very important. VSEPR theory gives us a good way of determining the shape. And so VSEPR theory is important. Now, after watching this video, you should be able to describe how the most stable configuration for a molecule is the one with the lowest potential energy. Given a molecular formula, you should be able to determine the electron geometry around each atom, the molecular shape, and all of the bond angles. And you should be able to describe how at high temperatures a molecule shape will deviate from the most stable one. And so VSEPR stands for valence shell electron pair repulsion. And it's a very simple theory. The basic idea is that the most important factor in determining geometry is minimizing repulsion. And so we've seen that the stronger the attraction, the more stable. We saw that with electron orbitals. We saw that with formation of bonds, with the formation of compounds. The stronger the attraction, the more stable. The stronger the repulsion, the less stable. And so if you have regions of electron density that are close, that's going to be unstable. And so VSEPR theory says that molecules will adopt the shape that minimizes the repulsion between electron regions. Now, when we talk about electron regions, a single region electron density can be a lone pair, a single bond, a double bond, or a triple bond.
Chemists use valence shell electron pair repulsion, or VSEPR theory, to account for the shapes of molecules. The theory is based on the idea that like charges repel each other until repulsions are minimized. The like charges in this case are the groups of valence electrons around a central atom in a molecule or ion. We'll represent them as bars attached to a sphere and show the electrostatic repulsions as yellow arrows of varying width. The simplest case has two negative groups around a central atom. At any angle less than 180 degrees, electrostatic repulsions push the bars apart. Repulsions are minimized when the bars attain a linear arrangement. Electron groups can be single bonds, as in gaseous beryllium fluoride, double bonds, as in carbon disulfide, triple bonds, as in hydrogen cyanide, or, as you will see shortly, lone pair.
And so please remember, a region of electron density can be a single bond, a double bond, a triple bond, or a lone pair. They all count as a single region of electron density. Now, there's three steps in determining molecular shape. The first is you determine Lewis electron dot diagram. Again, Lewis diagrams are very, very important. As long as you're doing chemistry, you're going to be doing Lewis electron dot diagrams, so please get very good at it. The second step is determine electron geometry. Now, this is really a pretty easy step. If you have two regions of electron density, then the electron geometry is going to be linear. If you have three regions, it's going to be trigonal planar. 4 regions, tetrahedral. 5 regions, trigonal bipyramidal. 6 regions will be octahedral. Now, octahedral, the oct comes from the 8 sides, and if you have 6 regions of electron density, you can imagine it forms an 8-sided object. But again, a single region can be a lone pair, a single bond, double bond, or a triple bond. And so to determine electron configuration or electron geometry is really pretty straightforward. Just count the number of regions around that center atom, and that will give you the electron geometry, electron configuration. Now, the molecular configuration is a little bit different. You're looking at just the atoms. And so the electron configuration, molecular configuration are only the same when you have no lone pairs on the center atom. If you have lone pairs on the center atom, then the two will be different. Molecular configuration or molecular shape, you're just looking at the atoms. And so for electron geometries, if you have two regions of electron density, that would be linear with a bond angle 180. If you have three regions, that would be trigonoplanar with a bond angle 120. Four regions, 1, 2, 3, 4, that would give you bond angles of about 109.5. That's tetrahedral. 5 regions is trigonal bipyramidal, and you have bond angles of 90, 120, and 180. And so for trigonal bipyramidal, it's like trigonal planar with one above that and one below that. 6 regions gives you octahedral. And so again, if you imagine planes connecting those points, that would give you an 8-sided object. You have bond angles of 90 and 180. And then 7 regions is pentagonal bipyramidal, and that gives you bond angles of 72 and 90. And so these are electron geometries. And again, you're looking at regions of electron density, which could be a single bond, double bond, triple bond, or a lone pair. Now, molecular shapes or molecular geometries are a little bit different because you do not count the lone pairs. So for instance, here we have angular. And so you can imagine, say you had trigonoplanar electron geometry, and this was a lone pair. And so electron geometry would be trigonoplanar. The molecular shape would be bent or angular. Or say you had tetrahedral electron geometry, and this top one was lone pair, then that would correspond to molecular shape of trigonal pyramidal and electron geometry of tetrahedral. And so again, electron geometry and molecular shape only the same when there's no lone pairs on the center atom. So you had trigonal bipyramidal electron geometry, and say this was a lone pair, then that would give you a seesaw molecular shape. Say you had 2 lone pairs, then that would give you a T-shaped molecular geometry or molecular shape. Likewise, if you had octahedral electron geometry and the bottom was a lone pair, that would give you square pyramidal. If you had octahedral electron geometry and you had 2 lone pairs above and below each other, that ends up with a square planar molecular shape. And so trigonal planar corresponds to having 3 regions of electron density.
3 negative groups attached to a central atom attain minimal repulsions in the trigonal planar arrangement, which has an ideal bond angle of 120 degrees. We observe this angle in molecules with 3 identical groups, such as boron trifluoride and sulfur trioxide. Molecular shape is determined by the positions of atoms, not electron pairs. Therefore, if one of the electron groups is a lone pair, the molecular shape is not trigonal planar, but bent or V-shaped. Since a lone pair is held by only one nucleus, it is less confined in space and exerts greater repulsions on nearby bonding pairs. As a result, the bond angle is less than 120 degrees, as you can see in this model of ozone.
And so non-bonding pairs take up more space, and so that makes the bond angle a little bit smaller. And so again, you look at ozone, you have a lone pair on top, takes up a little bit more space, pushes this atom down, and so this bond angle is going to be a little bit less than 120 degrees. And so trigonal planar electron geometry can correspond to trigonal planar molecular shape as long as there's no lone pairs on that center atom. If you have a lone pair, like in the case of ozone, then that gives you bent or angular molecular shape. Now, if you have 4 regions of electron density, and again, a single region can be a single bond, double bond, triple bond, or a lone pair, that would correspond to tetrahedral electron geometry.
Electron groups around a central atom attain minimal repulsions in a tetrahedral arrangement, which has an ideal bond angle of 109.5 degrees. The tetrahedral shape is very common, especially in organic molecules. An example is methane, the simplest hydrocarbon. With one of the 4 electron groups a lone pair, the shape is trigonal pyramidal. Since a lone pair exerts greater repulsions than a bonding pair, the bond angle is less than 109.5 degrees. Ammonia is a common molecule with this shape. Its bond angle is 107.3 degrees. When two of the four groups are lone pairs, the molecule has a bent or V shape. Two lone pairs exert greater repulsions than one, so the bond angle is reduced even further. Water, for example, has a bond angle of only 104.5 degrees.
And so 4 regions of electron density. Again, a single region can be a single bond, a double bond, a triple bond, or a lone pair. 4 regions correspond to tetrahedral electron geometry. But if you have a lone pair on top or anywhere, that would give you trigonal pyramidal molecular shape. If you have 2 lone pairs, then that gives you angular or bent molecular shape. And so you can actually get angular or bent by either having trigonal planar and 1 lone pair, or having tetrahedral electron geometry and having 2 lone pairs. And so again, electron geometry, you're looking at the regions of electron density around the center atom. Molecular shape, you're looking at the atoms relative to the center atom. And so we can make a table: number of regions, electron density, electron geometry, number of non-bonding pairs of electrons, and molecular shape. And again, notice that electron geometry depends only on the number of regions, electron density, which can be a lone pair, single bond, double bond, or triple bond. If the center atom does not have any lone pairs, then the molecular shape and electron geometry are exactly the same. And lone pairs tend to take up more space than just atoms because they're more diffuse. And so for trigonal planar, if you have trigonal planar electron geometry and molecular shape, you'd have a bond angle of 120. Now, if you add a lone pair, then the bond angle is going to be less than 120 because the lone pair takes up more space. For tetrahedral, if you have no non-bonding pairs of electrons in the center atom, you have tetrahedral molecular shape. You'd have bond angles of 109.5. If you have one bond angle, it's going to be less than, if you have one non-pair of electrons, non-bonding electrons on the center atom, it's going to be less than 109.5. Or if you have 2, it's going to be less than 109.5. An interesting question is, of these 3 molecules, which has the largest bond angles? And so we just saw that when you have lone pairs, they take up more space. And so the methane should have the largest bond angle. It's 109.5. The ammonia has hydrogen, nitrogen, and hydrogen bond angle 107, and the water is 104.5. Now notice that if we're talking about this bond angle here, what's important is electron geometry in the center of the atom. Of the center atom. If we're looking at this bond angle, again, what's important is the atom in the center of the angle. Now, bond angles will depend on the number of lone pairs. Again, if you have lone pairs, it takes up more space. But also the bond angles will actually depend on what the other atoms are. And so they will vary a little bit. If you have just one lone pair on tetrahedral, does not mean always you'll have a bond angle of 107 degrees. It depends on what the atoms are attached to the center atom. Also depends what the center atom is. A question could be asked: what is the oxygen-oxygen bond angle in ozone? And again, when you're asked about a bond angle, what you have to do is determine the electron geometry around the middle atom of the angle. And so first we draw the Lewis diagram for ozone. And so oxygen's in the 6th column. 3 times 6 is 18, so we have 18 valence electrons. Notice we get 2 resonant structures. The actual structure is an average of the 2 resonant structure. Now, for the bond angle, we just count the regions electron density. We have 1, 2, 3 regions, and so that corresponds to trigonal planar. Now, because we have a lone pair on the center atom, the bond angle is going to be a little bit less than 120 degrees. If there was no lone pair and oxygen was bound to the center atom was bound to the same type of atom 3 times, then it would be 120. But again, that lone pair takes up more space, pushes these atoms down, and so it's going to be less than 120 degrees for ozone. You could also be asked, what is the COH bond angle in methanol? And so again, when asked about an angle, you look at the center atom of the angle. So we're asked about COH, this angle. Now, from the Lewis diagram, it looks like that should be 180. But again, please remember the Lewis electron dot diagram does not represent the actual structure of the molecule. The Lewis diagram is just a 2-dimensional representation. Now the first step in determining the angle is drawing the Lewis diagram. We talked about formal charge, and we saw that hydrogen always has just a single bond. Oxygen likes 2 singles and 2 lone pairs. And so in carbon, remember, it likes 4 singles, it likes 2 singles and a double, a triple, a single, or 2 doubles. And so remembering the structures that have formal charge of 0 makes doing Lewis diagrams much easier. And so around oxygen, you have 4 regions: a single bond, double bond, triple bond, lone pair, all counted as a single region. And so we got 4 regions. So that gives us tetrahedral electron geometry. And so the COH bond angle should be a little bit less than 109.5. For tetrahedral, the bond angles are 109.5. Again, you got that lone pair, so it's going to be a little bit less than 109.5. You could also be asked about BF3. And so again, when you're asked about this angle, FBF, and so you're looking at the center atom of the angle. And remember that, for the formal charge, it's number of valence electrons free atom minus valence electrons, assuming bonding electrons equally shared. So for boron, you get 3 minus 3. For fluorine, you get 7 minus 2, 4, 6, 7. And so formal charge is 0, tell us that this is a stable structure. Remember, there are 3 exceptions to the octet rule. Boron and alumina often are happy with 6 valence electrons. Radicals, where you have odd number of electrons, you can't get noble gas configuration. And elements in the 3rd row and lower can have more than 8 valence electrons. And using the formal charge, we can understand those exceptions to the octet rule. And so we have our Lewis diagram. Now we got 3 regions around the boron, and so that means it should be trigonoplanar, and so that bond angle should be 120 degrees. And again, the Lewis diagram is just a 2-dimensional representation. It doesn't accurately represent it, and so from the Lewis diagram it looks like 90 and 180, but in actuality it is 120.
Electron pairs fill the valence level of a period 2 atom, but one from period 3 or higher can use d orbitals to expand its valence level and bond to more than 4 atoms. 5 electron groups minimize repulsions when they point to the corners of a trigonal bipyramid. Here we find 2 ideal bond angles. Equatorial groups lie 120 degrees apart, and axial groups lie 90 degrees away from equatorial groups. When phosphorus reacts with excess fluorine, the trigonal bipyramidal molecules phosphorus pentafluoride forms. Once again, when lone pairs are present, different shapes result. But a lone pair in an axial position creates 3 strong 90-degree axial equatorial repulsions, whereas a lone pair in an equatorial position creates only 2 90-degree repulsions. Therefore, to minimize the number of 90-degree repulsions, lone pairs always occupy equatorial positions. As before, lone pair repulsions reduce all other bond angles. With one lone pair, the object has a seesaw shape. Sulfur tetrafluoride is an example. With 2 lone pairs, the object is T-shaped, and the 2 remaining angles are less than the ideal 90 degrees. Bromine trifluoride is a T-shaped molecule. The final shape in the trigonal bipyramidal arrangement occurs when a 3rd equatorial lone pair repels the axial groups to 180 degrees. The object has a linear shape, as in the case of the triiodide ion.
And so elements in the 3rd row and lower can have more than 8 valence electrons. And so that's how we can get 5 regions of electron density. If we have 5 regions of electron density, that gives us trigonal bipyramidal electron geometry. Now, if we have no lone pairs on the center atom, then we also have trigonal bipyramidal molecular shape. Now, the trigonal bipyramidal shape is the only one that we'll really talk about, that the regions are a little bit different. And so Here, I think about this as a trigonal planar. It is trigonal planar, and then one above and one below. Now, if we put the lone pair on this position, it's referred to as axial position, then it's 90 degrees away from 3 other regions. And so that's a little bit too close. If you put the lone pair here on the equatorial position, then it's got a little bit more space. And so trigonal bipyramidal, the lone pair always goes equatorial first. And so that would result in a seesaw shape. Now, if you have 2 lone pairs, the second one also goes in equatorial position, and that gives you a T shape. If you have 3 lone pairs on the center atom, then all the equatorial regions are lone pairs, and that leaves you with a linear arrangement. And so the linear arrangement from trigonal bipyramidal electron geometry is kind of interesting, because even though you have lone pairs, the bond angles would be 180 degrees. And so the last one I'll talk about is where you have 6 regions of electron density. And again, you can have 6 regions because elements in the 3rd row of the periodic table and lower can have more than 8 valence electrons.
An arrangement has 6 electron groups attached to the central atom. Repulsions are minimized when the groups point to the corners of an octahedron and thus lie 90 degrees apart. Sulfur hexafluoride has an octahedral shape. Unlike the trigonal bipyramid, all positions are equivalent in an octahedron. So one lone pair can take any position to give the square pyramidal shape, with all bond angles less than 90 degrees. Iodine pentafluoride has this shape. To minimize repulsions, a second lone pair must lie 180 degrees from the first. The 4 remaining bonding groups are repelled to the ideal 90-degree angle and define the square planar shape. Xenon tetrafluoride, one of the first noble gas compounds to be made, is a square planar molecule.
And so if we have 6 regions of electron density, then we get the octahedral electron geometry. If we have no lone pairs on the center atom, that gives us octahedral molecular shape. Now, if we have a lone pair, it can take any of the 6 positions. So let's just imagine it takes the bottom one, and that gives us square pyramidal molecular shape. Now, if we have a second lone pair, it has to go opposite of the first. And so that would result in a square planar molecular shape. And so 5 regions of electron density gives you trigonal bipyramidal electron geometry. 6 regions gives you octahedral. So electron geometry only depends on the number of regions of electron density. And again, a single region could be a single bond, double bond, triple bond, or a lone pair. Lone pairs, if there's no lone pairs, then the molecular shape is the same as electron geometry. Lone pairs take up a little bit more space, and so it makes the bond angles a little bit smaller. And so a question you could be asked is, what's the molecular shape for phosphorus pentafluoride? And so first you have to do Lewis diagram. And so we would get something like this. And again, elements in 3rd row and lower, like phosphorus, can have more than 8 electrons. In this molecule, phosphorus is surrounded by 2, 4, 6, 8, 10. Now I can confirm this is a stable structure by calculating the formal charge. And so phosphorus starts with 5. If these bonding electrons are equally shared, it also has 5. So 5 minus 5 is 0. For fluorine, it starts with 7. If these bonding electrons are equally shared, then it's surrounded by 2, 4, 6, 7. And so fluorine also has a formal charge of 0. But again, please remember, elements in the 3rd row and lower, like phosphorus, can have more than 8 electrons. And so we got 5 regions, and so that would give us trigonal bipyramidal electron geometry. We have no lone pairs, and so that would also give us trigonal bipyramidal molecular shape. And so only when there's no lone pairs will the electron geometry and molecular shape be the same. We could ask, what is the oxygen-carbon oxygen bond angle in CH3COOH? And so first we have to determine the lowest electron dot diagram. And so this one's a little bit confusing. If you see the COOH, now that means that the oxygen is double bound to that carbon, and then you have a single bond to that oxygen and OH. And so it looks something like that. And again, drawing these diagrams, as long as you remember the most stable configurations for the atoms based on the formal charge, makes the Lewis diagrams much easier to do. And so we're asked about the OCO bond angle. And so you always look at the center atom of the angle, which would be this carbon. And we have 1, 2, 3 regions, and so that would give us trigonal planar electron geometry, and the bond angle should be about 120 degrees. And so the molecule looks something like that. With practice, you should be able to determine bond angles just by looking at Lewis diagrams. 3 regions, so that should be 120. 4 regions, that should be 109.5. Again, this is a two-dimensional representation. This thing up here shows it a little bit more accurately. 3 regions, that should be about 120. It's also kind of interesting, you can look at the shapes and you can see that some molecular shapes actually have all the atoms in one plane. And so if you have linear molecular shape, angular, trigonal planar, T-shaped, or square planar, all the atoms will be in the same plane. And so VSEPR theory is very cool, very powerful, very easy. The stronger the attraction, the lower the energy, the more stable. The stronger the repulsion, the higher the energy, the less stable. And so all that VSEPR theory says is that atoms will take the shape that minimizes the electron-electron repulsion. Makes sense. That's kind of interesting. If we look at molecule shape as a function of temperature, this bar here represents, I think, 5 picoseconds. So the molecule is actually moving really fast. And so if you look at room temperature, the molecule is in kind of the shape we'd expect, right? At this carbon, it has tetrahedral electron geometry, that carbon tetrahedral electron geometry. And then as we raise the temperature, we notice that it deviates from that tetrahedral shape greatly. And so higher temperatures, you have a greater deviation from the most stable configuration. But I hope that was helpful.